Welcome back. In the last video, we looked at this theorem right here that said that if I had a basis for a vector space with n elements, then any set with more than m elements had to be dependent. Any set with fewer than n elements couldn't span all of V, had to span something, a proper subspace, and any basis for V had exactly n elements. All right, so we'll prove a bit more. This is a corollary, which means that it follows from the theorem mostly. There's one direction that I think I need to make a bit more precise, so I'll do that. Let W be a subspace of a finite dimensional vector space. Then W is also finite dimensional. The dimension of W is less or equal to the dimension of V, and the dimension of W will be equal to the dimension of V exactly when W and V are the same. All right, so let's prove this. I'm going to start by assuming it's written right here. Assume that the dimension of W is equal to the dimension of V. We'll prove that these are the same. So I'm going to go by contradiction. So I'm going to assume that W is not equal to V. All right, notice that W is a subset of V, and so that means there exists an V in V minus W. All right, perfect. I know that BW, which is an basis for W, I know that this is linearly independent. I know that it spans W. And I know that it has n elements because we've assumed that the dimension of W is n. And now I know one more thing. I know that V is not in the span of BW because it isn't in W, right? I've taken V outside of W. Well, by theorem, the one from the end of section 1.4.1, so by theorem 1.4.3, I can look at BW union V. If I add V to it, since V is not in its span, it's still linearly independent. Perfect. But the number of elements in this set is n, I've added 1, so n plus 1, which is more than the dimension. By the last theorem, which was theorem 1.5.1, S is linearly dependent, which is a contradiction. And so what we've assumed at the start, that W was not V, is wrong. All right. So that tells us that the dimension tells us a big part of the story. The only subspace of full dimension of dimension n inside V are V itself.